Okay, hello there. This is Review Test 3, Calc 1. We're working with Chapter 4, and we just want to go through and show you some of the types of problems that will be similar to what you're seeing on the test. So starting with 4.1, we're looking at questions similar to 15 to 33 odd, and then 39 to 45 odd. So you can go in to your ebook or your real book or your WebAssign and find, see that there's a little number next to the problem you're doing. It usually corresponds to a book problem. So, just make sure you're practicing or taking a look at the problems that are similar to the ones I'm giving in this video. So, I'll do one, then go to the book and find one that's similar and try that. That's how you should practice for this test. Okay, so in 4.1, we introduce the idea of critical numbers. These are going to be the places where you have maxes and mins. And basically, critical numbers occur at places where the derivative does not exist or the derivative is equal to 0. So we're working with the derivative. Okay, so let's take the derivative, 4x cubed minus 8x. Right, so this thing exists everywhere, right? We don't have any issues with division by 0 or something weird like that. So no critical numbers there. The other place is when the derivative is equal to 0. So you set the derivative equal to 0 and solve. So we can factor out 4x and get x squared minus, 2. And it looks like we're getting a couple of critical numbers here. So you're taking the parts and setting them equal to 0. 4x equals 0, x is 0. And the other guy, x squared minus 2 is 0. Move the 2 to the other side. Square root property says x is plus or minus root 2. Okay, so it looks like we got 3 critical numbers there. And we know now we would take those and do sort of a graphical analysis with them. And the first derivative test, which comes in the next section. Okay. Anyways, let's look at another guy. So here's problem 21. F of t equals te to the negative 2t. Okay, this is going to require a product rule. There's also some chain rule in there. So f prime of t, I'll leave t alone. Then the derivative of e to the negative 2t is e to the negative 2t times the derivative of the exponent, which is negative 2. Then I'll take the derivative of this first part. So there's 2 factors in this product, right? You have to leave one alone, take the derivative of the other, and then take the derivative of the other and leave the other one alone. So here I'll have 1 for the derivative of t, and then e to the negative 2t. I'm going to simplify this a bit, write it so it looks nice. E to the negative 2t plus e to the negative 2t. Okay, great. So again, there's 2 places where these things have critical numbers. One place where the derivative does not exist. In this case, it does not happen. We basically have a bunch of continuous functions. The product of continuous functions are continuous. The sum of continuous functions are continuous. So this will never happen. No. Then you also want to look for where the derivative is 0. So in this case, negative 2t e to the negative 2t plus e to the negative 2t equals 0. We can factor out e to the negative 2t. And then you set the parts equal to 0. Let's carry on with that over here. So e to the negative 2t equals 0. Well, that never happens, right? There's no number you can put in an exponent to cause that thing to equal 0. The other one, negative 2t plus 1 equals 0. We can solve that. 2t equals 1. So t is 1/2. And we just have the one critical number this time. T is 1/2. Okay. One beginning application is finding mins and maxes on closed intervals. So to find the min and max on a closed interval, you have to analyze the function at the critical numbers and at the endpoints. Okay, so we get a problem like 34. So I sort of made my own. It's similar to the 34. H of t equals t all over t minus 2, and we want to find any we want to locate the absolute extrema on this interval, okay, from 3 to 5. Okay, so we need the derivative. So I'm going to do the product rule, low d high minus high d low, all over the low squared. Okay, so I'm going to get t minus 2 minus t all over t minus 2 squared equals negative t all over t minus 2 squared. Okay, so one thing, kind of in retrospect, we could look at this thing and note that the derivative is less than 0 everywhere. In other words, the function is always decreasing. So the max should be at the left-hand endpoint, and the min will be at the right-hand endpoint. Okay, but let's just pretend we didn't know that already, and look for critical points, right? So h prime of t does not exist where? Well, that'll be where the denominator is equal to 0. So where this thing equals 0, and clearly that happens when t is at 2. You plug 2 in there, you're going to get 0. Okay, so that's one critical number. Are there any others? So you also look for where this is equal to 0. But of course, if you try to solve that equation, which is essentially just setting the numerator equal to 0 eventually, so you multiply both sides by t minus 2 squared, you would have negative 2 equals 0, which is a false statement, which means there's no solutions to that problem. Okay, so in this case, it's opposite of the first two examples. Our critical number comes from where the derivative does not exist, and then we don't get anything from when the derivative equals 0. Okay, so at the end of this problem, then you have to check the original function, evaluate the original function at the endpoints and at the critical number. Okay. And I just realized the critical number isn't even in that interval, so we can exclude that point in our analysis and just look at the endpoints. So we'll have 3 all over 3 minus 2. So again, I'm working with the original function. You're looking for where is the largest y value and where is the smallest y value. Okay, so we have 3 over 3 minus 2, which is 3 over 1, which is 3. And then h of 5 is 5 all over 5 minus 2, which is 5 over 3. Okay. So the min value will be at, well, it's the 5, right? The min is at 5, 5/3, and then the max is going to be at 3, 3. Okay. Okay. Let's look at one more of those. So this is problem 41 in the book. We have f of x equals arctan of x squared on the interval from -2 to 1. And so again, you need the derivative, and then you need to find the critical numbers, evaluate the function at the critical numbers and the endpoints. So we have f prime of x is 1 over 1 plus x squared squared times the derivative of the guts, which will be 2x. Okay, so we'll have 2x all over 1 plus x to the 4th. We want the critical numbers, so f prime of x does not exist. That'll happen when the denominator is 0, but that'll never happen, right? You can't have an even power, raise a number to an even power and get a negative, so no help there. So no critical numbers there. And then you got to find, of course, where it's equal to 0. So in general, you could just set the numerator equal to 0 and solve. And it looks like we're getting 0 as a critical number. Okay, so we have to evaluate the function at the endpoints and the critical numbers. Okay, so I plug in -2, I'll have -4 all over 1 plus 16, which is 17. Plug in, I made the cardinal error, didn't I? I have to plug these into the original function. I apologize. Okay, so the first one will be arc tan of 4 The second one will be arctan of 0. That's just equal to 0, though. And then the third one will be arctan of 1. If you didn't know it, what the thing looks like, it looks like this. Okay, this arctan function, it should be symmetric. So I apologize there. There's asymptotes at pi over 2 and negative pi over 2, but it's increasing on its positive domain. Okay, in other words, the max will be arctan of 4, and of course you could use your calculator to figure that out, but I'm just going to write, the max is at negative 2 comma arctan of 4, and then the min will be at 1 comma arctan of 1. Okay, but you have your scientific calculator. You should be able to wait a second. That's not the min. Oh gosh, it's at 0, 0. It's at 0, 0. I should be calculating these. I don't know what's my problem. Okay, so there's that. Let's move on to the next section. So 4.2 was on some high-powered theorems and calculus. You had Rolle's theorem and then the mean value theorem. I'm just going to zoom in on the mean value theorem because Rolle's theorem is basically used to get the mean value theorem, so it's kind of like a helper theorem, and once you get mean value theorem, you really never use Rolle's theorem. So anyways, these problems are kind of like first determine if the mean value theorem can be applied, and then if it can be applied, find the value of C such that f of B minus f of A all over B minus A is equal to f prime of C. Okay, so here's number 45. So first on the test, you're going to say, is this thing continuous? And I don't need a proof of it, but is it continuous on the closed interval from -1 to 1? Okay, and sure, this is a polynomial. Polynomials are continuous everywhere, so you just write yes. Is it differentiable on the open interval? Differentiable on the open interval from -1 to 1. So usually for this, just get the derivative and see if you could just do plug in any of those numbers to get the value of the derivative. Okay. So f prime of x is going to be 3x squared plus 2. And certainly, I can evaluate the derivative by putting any of those values in between -1 and 1. I can evaluate the derivative everywhere. Okay, and it works everywhere. So yes, in both cases, those are true. So now what we want to do is so now find x or the c value. So find, that should be a c. It doesn't look like it, but there it is. Find a c such that f prime of c is equal to f of b minus f of a all over b minus a. Okay. So what is a and what is b? First off, those are the endpoints of this closed interval. Okay. So a is -1 and b is +1. Okay. So let's figure out what is that f of b minus f of a thing. So in our case, we have f of 1 minus f of -1 all over 1 minus -1, and I'm plugging that material into the function f of x that I'm putting in a box above. Okay, so f of 1, that'll be 1 cubed plus 2 is 3, minus f of -1, that'll be -1 minus 2, which will be -3, and that'll be all over 1 plus 1. 3 plus 3 is 6, all over 2, so that monstrous thing is 3. Okay, then you're going to set that equal to the derivative with a c in for x, right? So instead of writing 3x squared plus 2, you're going to write 3c squared plus 2, and then you set it equal to that 3 that you just found, and then solve for c. Okay, so you have 3c squared equals 1, c squared is 1 over 3, and so c is plus or minus square root 1/3. You want to make sure those answers are in the interval, and they both are in that interval. So those are your C values. Okay, Let's look at another example. So here we have f of x equals x to the 2/3, and we're working with the interval from 0 to 1. Okay, so first, is it continuous on this interval? Yeah, this thing is actually continuous everywhere. There's nothing you can't put in that function for x. So is it continuous on the closed interval then? Yes. Secondly, then the derivative. Does the derivative work on 0 to 1? And let's find the derivative. Okay, so f prime of x equals 2/3 x to the 2/3 minus 3/3 is minus 1/3. Okay, so we'll have 2 all over 3 cube root of x. Okay, this works everywhere except 0, and we don't care about 0. We just want the open interval from 0 to 1. So yes. Great. So continuous and differentiable. Now we have to find the c value. So we need to figure out what is that f of b minus f of a thing. This time a is 0 and b is apparently 1. Okay, so you can see above there when I first introduced the problem. Okay, so I need to do f of b minus f of a all over b minus a. F of 1 is just 1 to the 2/3. 1 to any power is 1. 0 to any power is 0 except 0. And then, yeah, it's over 1 minus 0. That's just 1. Okay. So I take the derivative. What do we have? 2 all over. I'm going to put a c in for x. And see if I can find that c value in between 0 and 1. Okay, so I'm going to multiply both sides by the cube root of c. Okay, so I end up with the cube root of c equals 2/3, and then cube both sides, and you get c. You know, you're raising both sides to the 3rd power. Okay, so c equals 8. 2 times 2 is 4, times 2 is 8. 3 times 3 is 9, times 3 is 27. So 8/27 is in the interval from 0 to 1, so that would be our c value that we're after. Okay. Okay, 4.3, we kind of get back to the first derivative issue and what we can do with the first derivative. So 4.3, I'm thinking of questions like 11 to 41 odd. Let me look back, make sure I gave you a number set. Yeah, 43 to 53 odd. Okay. Right, so in these problems, I want you to basically find the critical numbers. Do your sign chart. So on the test, I need to see your sign chart. You can't just magically come up with your answers. So do sign chart. In your sign chart, you should have test values. You should have your signs. And you should have your conclusions, just like I've been doing in the videos. So find the critical numbers, do your sign chart, and lastly, identify any relative extrema. And those should be given in the form of ordered pairs. Okay, so let's take a look at an example. F of x equals 2x cubed plus 3x squared minus 12x. Okay, so I need the derivative. F prime of x is 6x squared plus 6x minus 12. Okay. Where is this thing? Where does the derivative not exist? That never happens. It's a polynomial. Then figure out where it's equal to 0. Okay, so we got 6x squared plus 6x minus 12, 0. Factor out the 6. X squared plus x minus 2 is 0. And what do we get? X plus 2, x minus 1, 0. Set the factors equal to 0. And we're getting two critical numbers, -2 and 1. Okay, once you obtain those guys, you're going to go draw your number line. Okay, label your critical numbers. So you don't need to put anything except the critical numbers on your number line. Then you're going to do your test value, your sign, and your conclusion. Okay. Okay, so let's try some. So x equals -5, and we're plugging this into our derivative. Now I'm going to use this form down here. Okay, -5 plus 2 is negative. -5 minus 1 is negative, times a negative is positive, so it's going up. Try 0. 0 plus 2 is positive. 0 minus 1 is negative, so it's going down. Try 3. 3 plus 2 is positive. 3 minus 1 is positive. Positive times positive. It's going up. So we have, based off of the analysis, it's going up and then down around -2. So there's a hill there. In other words, max, relative max, technically, at -2, comma, f of -2. You could just write f of -2 if you want, but you literally have to take it and put it back into the function. So it would be -2, comma, and I haven't figured this out, so I don't want to do it. -8 plus 3 times 4 minus 12 times -2. -16 plus 12 plus 24. So 36 minus 16, 0, -220. Okay? And then the min value is going to be at 1 apparently. So at 1 comma f of 1, it should be 5 minus 12, -7. Okay. Okay, great. Let's look at a couple more examples of these, and then we'll move on to second derivatives. So this is number 35 in the book. So I have f of x is x plus 2 to the 2/3. Okay. F prime of x, you're going to bring down the 2/3. Then you have x plus 2 to the 2/3 minus 3/3 is minus 1/3 times the derivative of that, which is 1. With 2 all over 3 times the cube root of x plus 2. Okay. So first off, find where the derivative does not exist. And of course, that's going to be where the denominator is equal to 0, where this thing is equal to 0. And I think it's clear that's just at x equals -2. Okay. Where does the derivative equal 0? That never happens, right? So if you set the numerator equal to 0, it's a false statement. There's no solutions, so no help there. So our only critical number this time is at -2. So I'll go over and make my number line. And here's f prime of x. And then I need my test value, my signs, and my conclusion. Okay, so here we go again. X is -3. The numerator is always positive, so let's see what the denominator is. Denominator is negative, so this will end up being positive over negative is negative, and so therefore it is going down. Plug in x equals 0, and you get a positive over a positive. Positive going up, so there's going to be a relative min there. So we'll have a min at -2, comma, I guess 0. You plug that back in. You have to plug it back into the function, okay, not the derivative. So it gets a little confusing. You know, do I put it in the derivative? Do I put it in the function? Just try to keep that stuff straight. Let's look at another one. Problem 41. F of x is x squared all over x squared minus 9. And low d high minus high d low. So low times the derivative of the high minus high times the derivative of the low over the low squared. Okay, let's go down here. So we have 2x cubed minus 18x minus 2x cubed again, over x squared minus 9 squared. This will be then -18x all over x squared minus 9 squared. Okay. The critical numbers, And this is one of the reasons why I always say potential inflection points. These are kind of potential critical numbers, because technically we're going to consider the stuff from the denominator where the derivative does not exist, but the function also does not exist. So you can't really call them critical numbers, but we kind of use them in the analysis anyways. Okay, so f prime does not exist when x squared minus 9 squared, the denominator, equals 0. And clearly that equals 0 when x squared minus 9 equals 0. In other words, when x squared equals 9. In other words, when x equals plus or minus square root of 9, which is 3. So we still, even though these aren't really critical numbers, we use them on the number line. Okay. Okay. F prime of x equals 0. So that you take the numerator and set it equal to 0, and of course we get x is 0. So we have 3 critical numbers this time for our number line. -3, 0, and then 3. And then again, we got to go test value, sign, conclusion. Okay. Okay, so let's go at it. Plugging stuff now into f prime of x, which is this thing here. The denominator is always squared, so it's always positive. So therefore, the numerator is the deciding factor of whether it's negative or positive. So for instance, you try x equals -5. It'll be a negative times a negative in the numerator, which is positive, and that's your sign. Okay, so it's going up. -2, again, it's positive, it's going up. X is 1, that'll be negative, going down. X is 4, positive times a negative. -18 times +4 is negative, so again, it's going down. Okay, so there's only relative max here. There's actually asymptotes at -3 and 3, so there's nothing there with regards to maxes or mins. We have then a relative max at 0, whatever. So a max at 0, comma, I think it's 0, 0 if you plug in to the original function. Yeah, so if you, f of 0 is 0 squared is 0, all over 0 squared, which is 0, minus 9. So that's 0 over minus 9, which is 0. Yeah, okay, 0, 0. Okay, so you see a bunch of those. Then 4.4, we're working with the second derivative, and that tells us the concavity of the graph. So I'll be picking problems like 3 to 33 odd. And for these, I want you to find your points of inflection. And I'm probably not even going to worry about that, but I don't know. So, okay, so find your potential inflection points. And probably above, I should say, find potential critical numbers as opposed to just say find critical numbers, because we don't always just find critical numbers, right? So potential critical numbers, do the sign chart, identify relative extremis. So down here, we're finding potential inflection points. We do our number line. And this includes then test value again, sign, and conclusions. And then I think I kind of just leave it at that. I don't need you to identify inflection points. Maybe we should. ID inflection points. Okay, so instead of relative maxes and mins, we have inflection points in these problems. Okay, so let's look at some examples. So f of x equals x cubed minus 6x squared plus 12x. And now we're going after the second derivative. Okay. Prime is 3x squared minus 12x plus 12. F double prime of x then will be 6x minus 12. And then, right, so now the process is just the same as with the first derivative. Find where the second derivative does not exist. That never happens here because it's a polynomial. and then find where the second derivative is equal to 0. So it looks like 2. Then you'll go to your sign chart for the second derivative. Label your potential inflection points. This is an actual inflection point this time. Then get your test values, your signs, and your conclusions. And we'll go through our analysis. So x equals 0. And we're plugging this into the second derivative. So that'll be negative. And that means sad face. X equals 5. 30 minus 12, that's positive. And that means a happy face. Okay? So if the function is defined at the point and it changes from concave down to concave up or vice versa, that's an inflection point. So we have an inflection point at the point 2 comma f of 2, whatever that is. So you have to plug it back into the original function. In this case, it'll be 8 minus 6 times 4 plus 12 times 2. So 8 minus, I guess it's just 8. Okay, well, that's nice. So this is 2 comma 8. Okay, let's look at another. This one's a little harder in my opinion. We have f of x equals x times the square root of x plus 3. This has implicitly defined domain. We need to make sure x plus 3 basically is greater than or equal to 0. So our domain is going to go from -3 to infinity. And so when we go to our number line, we need not consider anything below -3. Okay, so we need the first and second derivatives. So I need to do, I need to do a product rule. Okay, so I'm going to leave x alone and then times 1/2 times x plus 3 to the -1/2, and then plus, what's the next guy? The derivative of x, right? And then I have x plus 3 to the 1/2. I'm going to take the second derivative. Again, I got to do a product rule on this stuff. So I'll have x times 1/2 times apparently -1/2 times x plus. So I'm doing a power rule here. To the -1/2 minus 2/2 is minus 3/2. And then plus, now you take the derivative of the x part, so that'd be 1 times the 1/2 times the x plus 3 to the -1/2, plus the derivative of this guy, so that's power rule. So bring down the 1/2, then you have x plus 3 to the 1/2 minus 2/2 is -1/2. These terms can be combined. They have the same, they're like terms basically. Let's clean this guy up as well. So I'll have -x all over 4 times x plus 3 to the positive 3/2 now. And then plus 1/2 of these plus 1/2 of those is 1 whole of those. So that would be 1 all over x plus 3 to the 1/2. I need to set it equal to 0 eventually, so I'm going to find a common denominator here and then simplify it so it's just easier to work with that way. So the second guy is missing a factor of 4, and it's also missing x plus 3 to the 2/2, or the 1 power, first power. Okay, so then my numerator will be -x plus 4 times x plus 3, in other words 4x plus 12, all over the new common denominator, x plus 3 to the 3/2. And then you're going to go 3x plus 12 all over 4 times x plus 3 to the 3/2, and now it's all ready. Okay, so first off, where does the second derivative not exist? That'll be where the denominator is equal to 0. And clearly that's going to happen when x is -3. Okay. And if you look at that, that is a true inflection point. So, well, it wouldn't even be an inflection point. It's right on the edge of the beginning of the function. So there's no way for it to change from concave down to concave up, because there won't be any concaveness to the left of this point. Okay, so that won't truly be an inflection point. So we could kind of just disregard that. We don't need to even look at that. So f double prime of x equaling 0, that's where the numerator equals 0. X equals -12, x equals -4. Again, this guy is not going to be basically in our domain, right? It's not something we're going to be looking at. Remember, the domain is from -3 to infinity. This thing isn't even there. So we can kind of just throw that away as well. Okay? So what happens? Do I go home? Am I done then? No, you're not done. You're still looking at the second derivative on its domain. It's just we don't have any critical numbers, or in this case, inflection points. Okay, it's just concave up or concave down on the whole interval. So again, you know, you do your test just like you always do. You have to do a test value, a sign, and conclusion. And this time we're working with the second derivative, which is sitting right here in red, in this red box. So I'll pick x equals 0, that's the easiest one, and that'll be positive, so it's concave up everywhere. Okay, let's look at a trig one and then one with a natural log, and we'll exit this section and go on. Okay, so a trig version 25. We have f of x equals sine of x over 2 on the domain from 0 to 4 pi. Okay, so we need the second derivative. F prime of x is cosine of x over 2. And then you need the chain rule, so times the derivative of x over 2, which is 1/2. F double prime of x, the derivative of cosine is negative sine of x over 2. You still have this 1/2, and then times the derivative of x over 2, which is 1/2. So our second derivative, -1/4 sine of x over 2. Okay. Okay. So again, does this ever not work? No. The sine functions are continuous everywhere, so we're good there. Don't have to worry about its derivative not existing, second derivative not existing. What else? Where is it equal to 0? That we have to do. So -1/4 sine of x over 2. We have a trigonometric equation here. Multiply both sides by -4. And then think about your unit circle, and where does sine actually equal 0? So that'll be at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, so n times pi. Okay? And then multiplying both sides by 2, so you're always taking the insides and setting it equal to your places. So x over 2 equals n pi, but then you have to solve for x, right? So it would be 2n pi, where the n is an integer. So counting number, negative counting number, positive counting number, or 0. Okay, so where do we have critical numbers in our interval? So our interval is from 0 to 4 pi. That'll be at 2 pi. It's the only real answer. 0, 2 pi, 4 pi, -4 pi, but they all have to be inside that interval. So the only one inside the interval is just 2 pi. So I'll go to my number line for my second derivative from 0 to 4 pi. Here is my only critical number inside the interval. And then we need to do test values and stuff. Okay. Okay, so test value, we'll try x is pi. And I'm plugging this into the second derivative, which is back here in red. sine of pi over 2, so you have to plug pi in for x, so sine of pi over 2 is 1, positive 1. Negative 1/4 times 1 is negative, so it's a sad phase. And then try x is 3 pi. So 3 pi over 2 is negative 1. Negative 1/4 times negative 1 is positive, so it's a happy phase. And there we have an inflection point. So this time we actually have an inflection point. So we have an inflection point at 2 pi, comma, f of 2 pi, and of course f of x was sine of x over 2. So 2 pi over 2 is pi, sine of pi is 0. Okay. Look, one more. So this one we have a logarithm. On the test, these are worth a little bit more. I think they're worth like 6 points. So make sure you don't just blow these off because it will ruin your grade. Okay. So I need the second derivative. The first derivative f prime of x is 1 minus 1 over x, or if you would rather, 1 minus x to the negative 1. Second derivative of 1 is 0. And then the derivative of negative x to the negative 1, bring down the negative 1, that would be positive 1, x to the negative 2, 1 over x squared. Okay. Okie dokie. This also has an implied domain, so I should, if I didn't say that earlier, the ln x function is only going to go from 0 to infinity. You can't put 0 or negatives into an ln x. Okay, so anyways, I'm going to be looking at that interval for my critical numbers, or sorry, my potential inflection points. And first off, where does the derivative not exist? And clearly that's at 0. 0 is not in the domain though, right? So what am I doing? How did I figure out it wouldn't exist there? I set the denominator equal to 0, right? That's not in our domain though, so we don't have to worry about it. And then does it, the second derivative ever equal 0? Well, you take the numerator and set it equal to 0, and no, okay? That has no solutions. So it's not going to have any potential inflection points. It's just going to have the same concavity throughout its domain. So from 0 to infinity, right? We got to do our test values, our signs, and our conclusions. So test value, try 1, right? 1 over 1 squared is positive. And so we are concave up on our entire domain. Okie dokie, great. So that does it for all that jazz. The next section, 4.5, is all about limits, infinite limits. So you're just going to, on the test, you'll see a whole helping of infinite limits. And here we go. So the limit as x goes to infinity of x squared plus 3 all over 2x squared minus 1. Okay. So the trick for these was to kind of remove everything except the high degree terms and then figure out that limit. Okay, so this will be the limit as x goes to infinity of x squared all over 2x squared. X goes to infinity of 1/2. And the limit of 1/2 is 1/2. Okay. Let's look at another limit as x goes to infinity of x all over x squared minus 1. So again, I'm just kind of collecting the high degree terms. And in the long run, that's all that really matters, of x over x squared. Infinity, simplify that, 1 over x, and then that's L over infinity, which is always 0. Okay. Let's do another one. So this one's a little tricky. X to negative infinity of x over the square root of x squared minus x. So again, just picking off the big parts there. And I put the limit as x goes to negative infinity of x all over the square root of x squared. The square root of x squared is actually the absolute value of x. And if you remember the definition of the absolute value of x, that's equal to negative x if x is negative, and positive x if x is greater than or equal to 0. right? In this case, we're looking at numbers going to negative infinity. So our numbers are going to end up being in the first part. You know, it's going to be negative x that we'll be using. So we can replace the absolute value of x with negative x because of the direction of the limit. Okay. And then we'll see that this is the limit as x goes to negative infinity of negative 1, which of course the limit of a constant is just a constant. Okay, let's look at another. So it's 31. Limit as x goes to infinity of x plus 1 all over x squared plus 1 to the 1/3. Okay, still the same game. You're just picking up the high degree terms. You have to be a little careful with the denominator. It's not x squared, it's x squared to the 1/3. Okay. So you'll have limit as x goes to infinity of x all over x squared to the 1/3 is actually, you just multiply the exponent, so that'll be x to the 2/3. It's all over x to the 2/3. Limit then as x goes to infinity, x to the 3/3 minus 2/3 is 1/3, and then the graph of that thing looks like this. Okay, so it's going to infinity. You could just put in 10 cubed, 100 cubed, 1,000 cubed, and when you plug it in, you'll get 10, 100, 1,000. So it's just getting bigger and bigger and bigger. 34. So we have a limit. Here's a trig one. As x goes to infinity of cosine of 1 over x. And what you kind of think of, how you think of this is basically, can you take the limit of the guts here? And yeah, that limit of 1 over x is just 0. And then you'll have the cosine of 0. And the cosine of 0, of course, is 1. One or two more. So 35. The limit as x goes to infinity of sine of 2x over x. This one you can't really finesse using any little tricks that we've learned in this section. What you have to do is the Squeeze Theorem, which you may have forgotten by now. But what's true for sine and cosine is that they always exist between negative 1 and 1. It's just a fact of life. And then you can divide everything by x. And you get negative 1 over x less than or equal to sine of 2x over x less than or equal to 1 over x. And then note the limit of the outer part. So the limit of negative 1 over x as x goes to infinity is 0. Then the limit as x goes to infinity of positive 1 over x is also 0. And basically our squeeze theorem said if the limit of the outer ones, if the limit of this and the limit of this equal the same thing, that forces the limit of the middle guy to equal whatever that same thing is. Okay, so all of that then implies that the limit of sine of 2x over x is actually just equal to 0. Okay? So that's by the squeeze theorem. Okay, sorry for spelling squeeze. Let's look at an example. This one is x going to negative infinity of 3 all over 1 plus 2 e to the x. So remember we had all these rules about limits going to infinity of exponentials. The limit of something like this is equal to the limit of its parts, supposing the limit of the parts equal something. Okay, so the limit of 3 is 3, the limit of 1 is 1. It just comes down to evaluating the limit as x goes to negative infinity of 2e to the x. Right? Okay, so what does that equal then? Well, what are you putting in? You're putting in, if you think about your table, you're putting in values going to negative infinity. Okay. So basically you'll have like 2e to the negative 10, which is the same as 2 all over e to the 10. Which is something really, really small. Okay, this will be 2e to the negative 100, which is really the same as 2 all over e to the 100, which is something really, really, really super small. 2e to the negative 1000 is the same as 2 all over e to the... It's getting really, really close to 0. Okay, so this thing is going to 0, and you can evaluate the limits of the other parts, so you just get basically 3 over 1 plus 0. Sorry. 3 over 1 plus 0, which is 3 over 1, which of course is 3. Whew. Okay, so expect a whole speckle of limit problems. Each one will be worth 4 points. Okay, so the beginning problems will all be worth like 5 points. These problems where you're finding critical numbers. Then the problems where you're finding a max-min on a closed interval, those are worth 5. MVT problems are worth 5. These number line problems are all worth 6. Okay. And then the limit problems are all worth 4. And then we'll have some sort of application from 4.7. We're not going to put 4.6 on there. It's just too time-consuming. Good stuff, but we don't have time for it this semester. So 11 to 21 odd. And we're thinking about maximizing functions. So you'll have some sort of constraint function, and then the function you want to optimize. You reduce the number of variables in the optimization function using the constraint function. Take the derivative, and the critical point is usually the value you're after. Okay, so anyways, let's look at something like that's similar to number 15. Okay, so find the point on the graph closest to the given point. So basically our constraint formula is this graph x squared. And the optimization formula is based off of the distance formula. So I don't know, we can't call it d because then we'll have the derivative of d. It just looks funny. So let's just call it g. Okay, so g of x is going to be x minus 2 squared plus y minus 1/2 squared. And then, so we use the constraint formula, which is at f of x, to reduce the number of variables in g of x. Really, it's g of xy, but then we're going to take this f of x and put it in for y. So I'll have x minus 2 squared plus x squared minus 1/2 squared. Okay. Take the derivative. I'm going to do power rule and chain rule, power rule, chain rule on the second one. So 2 times x minus 2. Plus 2 times x squared minus 1/2 to the first power times the derivative of the guts, which would be 2x. And that'll be 2x minus 4 plus 4x cubed minus 4x times 1/2 is minus 2x. And that'll end up being 4x cubed minus 4. Okay, so find the critical numbers. So set this equal to 0. 4x cubed equals 4. And then x cubed is 1. The cube root of both sides is just 1. So our point, hence the closest point, is the point to 1 comma, and then I need to put that back into the function 1 comma 1 squared, which is just 1. Okay. 1 comma 1. Great. So that's pretty much it. This application problem would be worth 5 points, whichever one I pick. Maybe geometry or something like that. Lots of good problems to pick from in that range from 11 to 21. I guess that's about it. So, you know, the test will be just like this review. There's not going to be any surprises. It'll be about the same length, same types of problems, same difficulty level. And, okay, so you know what you have to do, right? Okay, thanks for watching, and we'll see you next time.